All right, so here's some sample code that has a problem. I mentioned to you that this doesn't actually create a C string. It just makes a character pointer. And you can't, for one thing, you can't depend on the data in a string object to end in a null like you would a C string. So that's going to create a problem by itself. Other than the fact that we're creating a pointer to a structure that's inside an object, that's another no-no. But anyway, let's run this and see what we can figure out. All right, so we went through once, and it seemed to work okay. And then you're waiting for this to happen. So I'm going to put a break right there. Okay, so we're stopped right here. So we're going to step through this one instruction at a time. And I'm going to use step over. Step over is different from step into in that it won't go into a call to another function. So if anything that we're doing calls one of the standard C functions or whatever, we don't have to worry about falling into that function and getting lost if we use step over. So that's F10. So I'm going to hit F10. Okay, so that's interesting. GetLine didn't lock up on us. It didn't suspend what we were doing.
Right.
So that makes me think something screwy is going on. And we'll notice input string has the null string in it. Oh, I know why getLine did that. Because the last thing we did was a get for, or a extract for blee, which still had the new line at the end of it. So so we got a null string because there was immediately a new line. String has no characters at all in it, which means that when we try to reference input string 0, that's not a valid thing. Does that make sense?
Yeah.
So whatever address we get from input string 0, we can't depend on it because that's going to cause problems. So when we call get word count on input string, let's see what get word count is going to try to do. Well, you're trying to refer to characters in the string, and it doesn't have any characters in it. So because of the fact that you don't check for a 0-length string, so that's what's causing this problem.
Right, and on my first attempt at the thing, like I said, I used what we did in class, where I was using strings. I was doing the same thing when I went to go do that. Is it just that get line that's causing it?
Well, it's the fact that, for sure in here, it's the fact that you're not testing for an empty string.
Right.
And the reason you've got an empty string, well, there's two reasons you have an empty string. One reason you could have had an empty string anyway is if somebody just hit enter. So if I just hit enter the first time we do this, it's going to break the first time. Okay?
So I didn't test for it.
So you didn't test for a null string, which if you were doing the routine that we had, I think, yeah, right here, less than input length. Well, if length is 0, that loop is not going to run. Does that make sense?
Right.
So all of your, anywhere you're dealing with a string or a sequence, an array like that, you have to be sensitive to the case where it's empty and there are 0 elements in it. So looks like that's probably where the problem came from.
Yeah. So would it just be better to put the whole thing in if else statement and then test for if it's empty?
Well, if you're making a big loop like this, each phrase is going to be dealt with individually. And like I said, if the first thing I enter is hit is an enter,
right,
you're going to have an empty string to start with. That's what the problem is. It's not with your loop. It's not because you put a loop in.
Right.
It's because you
No,
didn't
I'm
handle.
saying should I put the whole code in like a diff and then test and see if it's an empty string and then put an output to say this is an empty string based on your string?
Well, that would work, or input length 0, or I mean, it would be valid to say if this is your word count code or your letter count code, and there are no letters in it, then it's not going to have that part. 0 words, 0 letters. I mean, get word count. You definitely should have something here that tells you when you're at the end of your string. Anytime you're incrementing through an array, you need to find out where the end is. You can't just blindly start incrementing and testing for values. All right, does that make sense? All right, well, shall we move on to chapter 9 then? Pointers and dynamic arrays. A pointer is just more or less the memory address of a variable, or actually, I would say a variable that refers to the memory address of another variable. Some operating systems that I've worked with call these indirect addresses, because it's not a fixed position. It's a way to get to some piece of memory. So it's kind of a cheat that allows us to look at any memory location not necessarily just ones that we have predefined. All right, so let's talk about how we get a pointer variable. So we declare a pointer variable by using asterisk. And it's a pointer to a variable of the type that we have at the beginning. So these are going to be integer pointers, P1 and P2. And we can have pointer variables and regular variables in the same code. We can actually refer to other variables and get their addresses with the address of operator. So if I set the pointer P2 to the address of V2, then when I refer to P2, if I'm referring to the contents of P2, it's going to be whatever is in the variable V2, in this case 2. And in fact, I could declare these all on the same line. Pointer variables are only going to be the ones that have the asterisk in front of them. If I want to refer to the contents of memory pointed to by a pointer variable, then I have to dereference that pointer variable. And that, when I'm using it in code, I dereference it by putting the asterisk in front of it. So the way I would read this statement here would be the contents of P2 is going to have the value 42 assigned to it. I'm sorry, P1. So asterisk in this situation is the dereferencing operator. Ampersand in this case is the address of operator. You remember where we used ampersand before was in parameters that are reference parameters, because it's the same situation. We're sending the address of another variable instead of having a new location that we copy values into. All right, so let's look at this code. P1 equals new int. New int. New is the way we create a dynamic variable. The new operator allocates memory for a variable of some type and returns the address to that new memory it allocated, and we can store that in a pointer variable. So P1 is a new integer. Let's set the value pointed to by P1 to 42. And let's set the address that P2 points to be the same address that P1 points to. Whenever you're using pointer variables, if you assign a value to a pointer variable, you're assigning a value to the address that it's pointing to. So this makes P2 point to the same address as P1. So now if we output asterisk P1, what does that mean? Ms. Hargrove.
42.
We're going to output 42 because
It was assigned the
that's the contents of the memory that P1 is pointing to. And what if we output asterisk P2, Ms. Hernandez? It's also going to output 42 because P2 points to the same address that P1 points to. And we already know the contents of that memory is 42. All right, so now we're going to set asterisk P2 to 53, and we're going to output the contents of P1 and the contents of P2 again. What's going to happen there, Mr. Gear?
42 and 53.
Okay. You said P2 is going to have 53 in it,
Right.
but you think P1 is still going to have 42 in it? What did I say happened here?
It ties it to the same address.
They both point to the same memory address. So if I change the contents of the memory address that P2 is pointing to, and P1 points to the same address, they'll both be 53. Now I make another new int and point P1 to that and set its contents to 88. Now I output the contents of P1 and P2. Ms. Hargrove, what are we going to get this time?
P1 is 88, P2 is still 53.
All right. Now P1 points to a new address, and P2 still points to the old address. The new address we're going to set to 88. The old address still has 53, so we're going to get 88 53. That makes sense to everybody. Pointers are a little tricky. They have a diagram on page 512 that you can look at. Let's look at page 512. So here they've drawn a little diagram. P1 and P2 in this example are originally pointing to different memory locations, one of which has 84 and one of which has 99 in it. When we set P1 to P2, now P1 and P2 are both pointing to the same memory location, and it's the one that had 99 in it before. Start in the same part, and we set the contents of P1 to the contents of P2. Even though they're pointing to different memory locations, they both are 99 now, but I can still change them independently. And then there's another display 9.3 on page 515 that is intended to show you what's happening in the code that we just looked at. So we have P1 and P2 that are pointers. They don't point to anything until we create some new integer, a dynamic integer variable that P1 now is going to point to, and we set it to a value. We then set P2 to P1, and now they both point to that same memory location with a value in it. We set P2 to 53. Since they're both pointing to the same memory location, there's only one memory location there, it becomes 53. Now we create another new integer that we point P1 to. It has garbage in it because we didn't initialize it. Now we set it to 88, and now we have P1 pointing to a memory location that has 88 in it, P2 pointing to a memory location that has 53 in it. And that's what happened. Ms. Hernandez, number 2 on page 515. What unfortunate misinterpretation can occur with the following declaration? Int asterisk int pointer 1, int pointer 2. What does that look like we're declaring there? All right. So because it's named int pointer 1 and int pointer 2, and we start the line with int asterisk, if you're not sure quite what's happening, you might think they're both pointers to integers, but they're not. The syntax is just ignoring white space. The asterisk goes with the very next variable that we declare. So the first one is a pointer to an integer. The second one is an integer. If you think you're declaring two integers this way, you're not. But we usually put the asterisk just ahead of the name to make it clearer what we're doing. All right, Mr. Gear, number 3, 2 uses of the asterisk operator that are relevant to us in this chapter, and what is it doing?
In space asterisk P1, and it's declaring a pointer.
Okay.
And then asterisk P1 equals 42, and it's saving that memory location.
What do we call that use of the asterisk?
Declaration.
The second one would be the dereferencing operator. All right, Ms. Hargrove, what is the output produced by this code?
The first output would be P1 is 10 space P2 is 20.
Okay, 1020.
The second set of output P1 would be 20 space P2 would be 20.
Okay, 2020. And then
P1 would be 30 and space P2 would be
3030. So 1020, 2020, 3030. And what if we changed and replaced the P1 equals 30 with P2 equals 30 instead? How would that change the output?
Well, if they're both pointing to the same reference, then it's still.
So it would not change the output.
We're not.
Because, I mean, all we're doing is changing the contents of the memory location to 30. It doesn't matter whether we're using P1 or P2 because they both point to the same memory location. One more, Ms. Hernandez. What is the output produced in number 5?
P1 would be 10 space 20.
All right, 1020.
Second is the 20 space 20.
Okay, 2020 again. And the third output?
Is 30 space 20.
3020. So this time, instead of changing the address that P1 is pointing to, we're just changing the contents of the location P1 is pointing to. And if we change it to something else, it's not going to affect P2 because P1 and P2, in this case, are still pointing to different memory locations. When we use the new operator, we're using something called the free store or the heap. It's memory that's part of our program that is free for us to use in our code, allocate to do different things. Probably any programs that you work on in here will not get complex enough that you're going to use up the heap. But if you've ever had a program crash with a heap overflow, that's the reason. All of the memory that was allocated to that program got used up. So it's good programming practice to manage that memory. And so we would like you to return that memory back to the heap when you're through with it. The way we do that is with the delete operator. So after you've used your pointer, you've created a dynamic variable with new. Once you get done with it, you should return it to the heap by using the delete operation. So in this case, we've got, well, in this case, we don't need to because we're not referring to any dynamic memory. But if we're referring to dynamic memory, once we get done with it, we should delete that variable to return the memory back to the heap. Once we have done a delete, we have a situation known as a dangling pointer. That pointer no longer actually references anything. So if we were to try to use it, maybe not immediately, but at some point in our program, trying to use it is liable to produce bad results. So don't try to use a dangling pointer for anything. One that's not, doesn't have a valid address that it's pointing to. When you create a new variable with the new operator, it's called a dynamic variable. Once upon a time in C, there were things called static variables. That's not a terminology that we actually use these days much. We typically we call them something called automatic variables because their properties are controlled for us. We don't have to worry about when memory gets allocated and what to do about it. So you may hear them referred to as automatic variables or ordinary variables. So in this case, y would be an ordinary integer variable. We create a new integer variable, a dynamic integer that we point to with x. And we mentioned global variables when we talked about creating global constants. Global variables are typically frowned upon, and I hope you don't run across them, but it just means that they're declared outside of any function and are therefore accessible from any function, which means that any function can alter them, and you never know when that's going to happen because it can be altered outside the scope of your code. So that makes them dangerous. You may also find that useful to declare or define pointer types so that you don't have to worry so much about where the asterisk goes and when you use it. And so we have something called typedef, which allows us to create a name for a type. The place it's most useful is to name a pointer type. So in this case, they've named a pointer to integers type as int pointer. Now when we declare int pointer p, q, r, s, t, I don't have to worry about putting an asterisk in front of each of them because the asterisk that indicates that the pointer is part of the int pointer type. And the other case where it can be useful is if you are you have a reference variable that's a pointer variable. You can easily get confused about where an asterisk and an ampersand both go in that bottom of page 519. Couple more self-test exercises, and we'll take our break. Bottom of the page 520. Mr. Gear, suppose we create a dynamic variable p. Pointer p points to a new character. The variable that we created is being used. Now we're done with it. How do we destroy that dynamic variable and return the memory to the free store or the heap?
Delete p.
Delete p. All right. Ms. Hargrove, write a definition for a type called number pointer that will be the type for pointer variables that hold pointers to dynamic variables of type int. And then a declaration for a pointer variable called myPoint that is of type number pointer.
Typedef. INT. Apostrophe. The number of PTO.
All right. And now how would we declare a variable of type number pointer?
It'd be a number pointer. And, is a monthly?
My point. Okay? Ms. Hernandez, how would you describe describe the action of the new operator and tell me what it returns?
New operator takes type for its argument and allocates new space or space on the restore
Okay, and what does it return?
to the memory.
Returns a pointer to the memory that it allocated. So it allocates space for whatever data type that we're creating, and it returns a pointer to that space so that we can store it in a pointer variable. All right, let's take a short break. We'll continue in about 5 minutes.